In the winter of 2018, meteorologists in the United States recorded more than 100 lightning strikes during a single snowstorm across the Great Lakes region. By the end, you will understand why the popular story about thunder and snow, run immediately or face certain danger, is both incomplete and often wrong. People repeat the same line every winter. If you hear thunder during a snowstorm, run. The phrase sounds dramatic and urgent. It spreads easily through weather alerts, social media, and survival advice. A lesser-known fact is that the phenomenon called thunder snow has been documented since at least the 1800s, yet it remains rare enough that most people never experience it firsthand. Because it is rare, the mind fills the gap with assumption. Rare events often get exaggerated. Another overlooked detail is that thunder snow occurs in less than 1% of winter storms worldwide, which means most people talking about it have never actually seen it. The belief grows stronger because thunder normally belongs to summer storms. When the sound appears in winter, it feels unnatural. A quiet fact that often surprises people is that snow can actually dampen the sound of thunder by up to 30%, making strikes seem closer than they are. So the myth forms: thunder and a snowstorm equals immediate catastrophic danger. The reality is more complicated. A hidden detail is that the biggest risks in such storms usually come from visibility collapse and rapid snowfall rates, not lightning itself. The claim people repeat sounds simple. Thunder means lightning. Lightning means you are in mortal danger. A rarely mentioned statistic is that less than 10 people per year worldwide are struck by lightning during snowfall events, compared to thousands during summer storms. This belief sounds reasonable because lightning is dangerous. In a typical summer thunderstorm, temperatures, moisture, and unstable air create strong vertical currents. But a lesser-known atmospheric constraint exists. Winter air holds far less moisture than summer air, which dramatically reduces the electrical charge that can build inside clouds. The missing detail is the structure of the storm. Most winter storms form through large-scale atmospheric lifting rather than localized convection. A quiet meteorological fact is that thunder snow only forms when narrow convective bands develop inside a broader snow system, something that happens in very specific conditions. When those bands appear, lightning becomes possible, but lightning in snowstorms behaves differently. Another overlooked reality is that winter lightning tends to produce fewer strikes, but often stronger individual bolts, because charge separation occurs in colder, denser air. Imagine a soldier on a winter march in Eastern Europe during the winter of 1944. The wind is blowing sideways snow across a road that barely exists anymore. A lesser-known wartime detail is that during the Battle of the Bulge, snowfall rates sometimes exceeded 5 centimeters per hour, creating whiteout conditions long before thunder mattered. Someone hears thunder in the distance. The instinct might be to run, but in deep snow, running means exhaustion. A logistical truth of winter warfare is that moving quickly through snow deeper than 30 centimeters can double the energy expenditure of a soldier carrying gear. Running might actually increase the danger. Visibility is collapsing. Units are already spread thin. A rarely discussed constraint is that during heavy snow, sound carries unpredictably, causing thunder to appear closer or farther than its true distance. So the myth fails immediately in the real world, not because lightning is harmless, but because the situation around it is misunderstood. Another claim appears often: thunder and snow means the storm will suddenly become deadly. The reasoning sounds logical. Thunderstorms in summer often bring violent winds and rain, but a lesser-known meteorological fact is that thunder snow is more closely associated with intense snowfall than with destructive winds. The missing piece is the vertical motion inside the cloud. Snowstorms with thunder have strong upward currents. A technical reality is that these updrafts can reach speeds of 20 to 30 meters per second, similar to moderate summer thunderstorms. That vertical motion produces lightning, yet the greater effect on people at the ground is snowfall intensity. A quiet statistic reveals that thunder snow bands can produce snowfall rates of 5 to 10 centimeters per hour, enough to bury roads rapidly. Picture a highway convoy trapped in a storm. The thunder cracks above the cloud deck. People panic because of lightning, but the real threat is accumulation. A lesser-known operational issue is that snowfall rates above 5 centimeters per hour can overwhelm plowing operations in under 30 minutes. Vehicles stall, engines idle until fuel runs out. Another overlooked reality is that in severe winter storms, carbon monoxide poisoning inside stalled vehicles kills more people than lightning ever does. The thunder becomes a psychological trigger rather than the primary hazard. A different myth appears in survival advice. Thunder in snow means the storm will become a blizzard. It sounds convincing because both phenomena involve intense weather, yet a technical fact complicates that idea. A blizzard is defined not by snowfall, but by sustained winds above 56 kilometers per hour and visibility below 400 meters for at least 3 hours. Many thundersnow events do not meet that definition. A lesser-known observation from meteorological records shows that some thundersnow storms occur with relatively light surface winds, especially near large lakes. Why lakes? Because temperature contrast matters. A hidden driver of many thundersnow events is lake effect convection, where cold air crosses warmer water. In fact, over 70% of recorded thundersnow events in North America occur downwind of the Great Lakes. That warm water fuels instability. The snowbands intensify, lightning forms, but the surface wind may remain moderate. The myth collapses once again. Imagine a radar station tracking weather during a winter exercise. Operators see narrow bands forming over Lake Erie. A lesser-known technical constraint is that lake effect snowbands can be only 10 to 20 kilometers wide, but stretch more than 150 kilometers in length. Inside that band, snowfall becomes extreme. Outside it, almost nothing falls. Soldiers 10 kilometers apart experience completely different storms. If someone hears thunder and runs blindly away from the sound, they might actually move deeper into the snowband. Another belief spreads across winter survival guides. Thunder in snow means the temperatures are about to rise dramatically. The logic seems simple. Thunderstorms usually occur in warm air, but a meteorological detail rarely mentioned is that thundersnow often occurs when surface temperatures are between -5 degrees Celsius and -1 degree Celsius. That temperature range allows strong atmospheric lifting while still producing snow. Another hidden constraint is that ice crystals collide with grapple, soft hail-like particles, to generate electrical charge inside the cloud. Without grapple, lightning becomes unlikely. Grapple forms when supercooled water freezes onto snowflakes. A quiet microphysical fact is that grapple particles typically measure between 2 and 5 millimeters in diameter. Those collisions drive charge separation. Lightning follows, but temperature at the surface may barely change. Picture an artillery unit stationed in mountainous terrain during winter. Thunder echoes across the valley. Some soldiers assume warmer air is arriving. A lesser-known operational risk is that temperature shifts near the freezing point dramatically increase the likelihood of ice accumulation on equipment. Ice buildup disables radio antennas. Another rarely discussed detail is that wet snow can triple the weight load on power lines compared to dry snow, increasing failure rates. So thunder does not signal warmth, it often signals intense precipitation. Another story people repeat: lightning during snowstorms is impossible, therefore thunder must be something else. For centuries, people believed the sound came from collapsing ice sheets or distant avalanches. A historical meteorological note reveals that scientific confirmation of thundersnow became widely accepted only in the mid-20th century when weather radar improved. Before radar, observers lacked evidence, yet lightning had always been there. A lesser-known historical observation comes from Arctic explorers in the 19th century who documented thunder during polar storms, long before modern instruments confirmed the mechanism. The myth survived because the phenomenon is rare. Another statistical fact shows that in some regions, a person might experience thundersnow only once every 10 to 15 years. The rarity created mystery. Now imagine a winter convoy crossing a mountain pass. Snow falls steadily. Thunder echoes through the peaks. A lesser-known acoustic effect is that mountain terrain can reflect thunder, making a single lightning strike sound like multiple.
People may believe multiple strikes are occurring. In reality, it may be one bolt. Running downhill blindly during a storm risks avalanches. A crucial winter safety fact is that heavy snowfall combined with sudden loading can trigger slab avalanches within hours of accumulation. So the instinct to run becomes dangerous again. Another myth suggests thunder means lightning will strike the ground directly nearby. It feels logical because thunder follows lightning closely in summer storms, but an atmospheric fact complicates that assumption. Lightning in snowstorms often occurs within clouds rather than striking the ground. In fact, cloud-to-cloud lightning dominates winter storms, sometimes making up more than 70% of discharges. The thunder still reaches the ground, the lightning often does not. A hidden constraint explains this. Snowstorms typically have lower cloud tops than summer thunderstorms, sometimes only.
In February of 1978, during a powerful winter cyclone across the American Midwest, weather stations logged more than 200 lightning strikes inside a single snowstorm system. By the time the storm ended, highways were buried, more than 50 people had died, and almost none of the fatalities had anything to do with lightning. By the end, you will understand why the familiar advice, "If you hear thunder in a snowstorm, run," misses the real mechanics of danger. The common story is simple. Thunder equals lightning. Lightning equals immediate threat. A lesser-known meteorological statistic is that over 90% of lightning injuries occur between May and August, not winter months. Yet the phrase spreads every winter. It sounds urgent, cinematic, and easy to remember. Another quiet fact is that human perception treats rare combinations of events as more dangerous than common ones, even when statistics show the opposite. Thunder and snow together feel unnatural. Summer storms train people to expect thunder before heavy rain. But a hidden atmospheric detail is that snow crystals scatter sound waves, which can make thunder seem softer but closer than it actually is. The mind interprets the sound incorrectly. People assume lightning must be directly overhead. Another rarely mentioned measurement shows that thunder from winter lightning can travel more than 20 kilometers through cold, dense air. So the first assumption breaks immediately. Hearing thunder does not mean the strike occurred nearby. But myths persist because they are easy to visualize. When thunder cracks in a silent winter landscape, instinct tells people to move fast. A lesser-known physiological fact is that deep snow can increase metabolic energy use during walking by 40 to 60% compared with dry ground. Running through snow burns even more energy. The survival advice begins to collide with physics. Consider a winter patrol moving through forest terrain. Snow is knee-deep. The temperature is -7 degrees Celsius. Thunder echoes somewhere beyond the hills. A lesser-known operational detail from cold weather training manuals is that exhaustion during snow movement can reduce body temperature by several degrees within an hour if clothing becomes damp. Running becomes a liability rather than protection. Another belief appears frequently. Thunder during snow means lightning will strike the tallest nearby object. People imagine trees, towers, or buildings becoming immediate targets. The reasoning comes from summer thunderstorm behavior, yet a hidden atmospheric constraint changes the pattern. Winter storm clouds are structured differently. A technical observation from lightning detection networks reveals that winter lightning often originates from lower altitudes, sometimes only 4 to 7 kilometers above ground. Because of that, charge separation inside the cloud becomes weaker and more chaotic. A lesser-known electrical fact is that winter lightning flashes are often shorter in duration but can carry higher peak currents than summer flashes. So the strikes behave differently. Many remain inside the cloud layer. Imagine a rural town during a heavy snow band. Thunder rolls above thick cloud cover. People inside houses assume lightning will strike their roofs. A rarely discussed infrastructure fact is that modern power grids experience fewer lightning-caused outages in winter than summer, even in regions with frequent snowstorms. Snowstorms cause blackouts mostly by weight, not electricity. Wet snow accumulates on branches and cables. Another quiet engineering reality is that 10 centimeters of wet snow can add more than 20 kilograms of a single meter of power line. Lines sag, trees snap, the power fails. The thunder becomes dramatic background noise, while the real damage comes from gravity. Another myth grows out of survival advice. Thunder means the storm has become unstable and unpredictable. The claim sounds correct because thunderstorms involve unstable air masses, but instability in winter storms behaves differently. Large snowstorms are driven by large rotating low-pressure systems called mid-latitude cyclones. A hidden structural fact is that these storms often stretch more than 1,000 kilometers across, far larger than typical summer thunderstorms. Inside that massive circulation, narrow corridors of rising air form. Meteorologists call them mesoscale snow bands. A lesser-known radar observation shows that these bands can produce snowfall rates 3 to 5 times greater than surrounding areas. Lightning tends to form inside those bands. The thunder you hear is actually a marker of where the heaviest snow is falling. Picture a highway during such a storm. Visibility is already reduced to 200 meters. Suddenly, thunder cracks overhead. Drivers panic because lightning feels dangerous. But a rarely discussed traffic statistic reveals that multi-vehicle pileups during snowstorms are most strongly correlated with sudden visibility drops, not thunder or lightning. Snowfall intensity blinds drivers first. When heavy bands move across a road, visibility can fall to near zero within minutes. Another lesser-known observation from highway safety studies shows that whiteout conditions can reduce driver reaction distance to less than 10 meters at highway speeds. The thunder may arrive at the same moment, but it is not the cause. Another popular claim says thunder and snow means the storm will produce record accumulation. The logic is simple. Lightning means stronger storms. Yet meteorological records show a more complicated pattern. Some thunder-snow events produce extreme snowfall, but others do not. A lesser-known climatological fact is that many thunder-snow reports occur near coastal regions where warm ocean air interacts with cold continental air. These areas produce instability without necessarily producing massive snow totals. For example, coastal cyclones sometimes generate lightning above offshore waters, while inland snowfall remains moderate. Another overlooked atmospheric detail is that sea surface temperatures can remain 10 to 15 degrees warmer than surrounding winter air, fueling convective clouds above the ocean. Thunder forms there first. People on land hear the sound and assume the snowstorm has intensified. In reality, the electrical activity may be occurring dozens of kilometers away. Now imagine a naval patrol in cold waters during winter operations. Snow falls lightly. Thunder rolls across the horizon. A lesser-known maritime meteorology fact is that lightning detection over oceans reveals far more winter strikes than were historically recorded on land, because ships carry instruments while many coastal areas do not. The thunder does not always mean the storm above you is changing. Another myth suggests thunder during snowstorms means a sudden atmospheric collapse, an idea rooted in older folklore. Farmers once believed thunder in winter meant the storm would clear quickly afterwards. The belief appears in agricultural diaries dating back centuries. But modern weather analysis tells a different story. A hidden timing pattern exists. Thundersnow most often occurs near the strongest upward motion inside a storm's comma-shaped cloud head, the region where precipitation is most intense. In simple terms, the thunder arrives when the storm reaches maximum strength.
A lesser-known radar study conducted during several North American blizzards found that lightning bursts frequently appeared 30 to 60 minutes before the highest snowfall rates were measured at the surface. So thunder sometimes acts as an early signal of worsening snow. Picture a city emergency center watching radar screens. Lightning flashes appear in the snow shield. Operators know what that means. A rarely discussed operational procedure is that transportation departments often dispatch additional plow crews when lightning appears in radar bands because it suggests heavy accumulation is imminent. The thunder warns them, but not about lightning danger. It warns them about snow. Another myth focuses on temperature. People assume thunder means the atmosphere is warming rapidly. That belief comes from summer thunderstorms, where warm, humid air drives convection. But winter storms break that pattern. Thundersnow frequently forms near the freezing point, but not always above it. A hidden thermodynamic detail is that temperature layers inside winter storm clouds can range from -10 degrees Celsius to -20 degrees Celsius, where charge separation occurs. These cold layers produce grapple particles. Grapple, soft ice pellets, play a crucial role. A lesser-known cloud microphysics fact is that collisions between grapple and ice crystals create the electrical imbalance needed for lightning. Without those collisions, the storm remains electrically quiet. That means thunder is actually evidence of complex microphysical processes happening kilometers above the ground. Consider a mountain weather station measuring snowfall during such a storm. Instruments record rapid accumulation. Thunder echoes through the valley. A rarely discussed measurement challenge is that strong snowfall can interfere with radar signals, causing underestimation of precipitation.